Okay, hi. So we're going to go ahead and go over 1680. So this is the corresponding problem to 1679, which we talked about on Friday. But I'm actually going to go over all parts of it because there was something different that happened in each one of them. So let's go ahead and just start right away with NAF here, right? So the question said, use the appendix from data D, calculate the OH minus and the pH concentration. Of course, we know that NAF is a salt, so that means we have to do this thing where we break up the salt into its ions. Figured out how to go in full screen and write a little bit thicker. NaOH, HF, strong base, weak acid. This is going to be a basic solution. Okay, because strong base, weak acid. Now we know that when we are looking at a salt solution like this, we focus on the weak side, so I'm focused here. But my solution is basic, so between F minus and HF, I have to focus on the base, which is F minus. I'm going to go ahead and write a base equation. I'm going to, go ahead and ice it. One to one, so 0.105. Remember, any questions, pause and ask. So I know that my KB, and I need a KB here, is x squared over 0.105 minus x. Now I need a KB because I just wrote a base equation. I flip to Appendix D. Turns out the information that I have is a Ka for HF. And that Ka was 6.8 times 10 to the negative fourth. So I went ahead and I used Ka times Kb equals Kw. Remember, I always know Kw. And I get the Kb, which is for F minus now. And that is 1.5 times 10 to the negative 11th. So I just jump back down here. Gonna make my approximation because that's a small, whoa, got it, okay. I was saying that I was gonna make my approximation since I have a small k. This is not x squared, it's just gonna be x. Turned out to be 1.2 times 10 to the negative 6th molar, which is my concentration of OH minus. So that was one of my answers. I took the negative log of that number, and I got the the POH to be 5.9. 14 minus the POH gives me the pH, and I got to be 8.1. Okay, so that should be quite straightforward. Again, broke up my salt into its ions, analyzed them, figured out I was going to have a basic solution. Basic solution meant I needed to write a base equation from my weak side. So that was F minus. Did that. Needed a KB. Looked in the appendix. Didn't have a KB for F minus, but did have a Ka for its acid, right? F minus is the conjugate base of HF. So found that Ka. Used Ka times Kb to get to Kw. Solved for Kb, came in here and plugged in, solved for X, which was my OH minus concentration. Negative log of that gives me pH. 14 minus that gives me, negative log gives me POH. 14 minus that gives me pH. Feel free to pause now, ask each other questions, or just if you need time to catch up and do your writing or whatever. Okay. All right, I'm going to go ahead and scroll down here. 0.080 molar Na2S was the next problem. So 0.080 Na2S. Okay, so just start like normal. Break into its ions. Strong base, weak acid. Now I got this H2S by crisscrossing H plus with S2 minus, and H2S, which I know is actually an acid, but it is a weak acid, so strong base, weak acid means this is going to be a basic solution. Basic means I focus on this side because it's the weak side, and basic means I need to choose the base between S2 minus and H2S. So that's obviously S2 minus because H2S is an acid. Okay, but now notice here, when I go to write my equilibrium, whenever we do this adding an H2O, what we're doing is plucking off one H plus from an H2O. So if I just pluck off only one H plus, this S2 minus does not become H2S. Instead, it becomes HS minus. And that's what I need to do here. I need to recognize that H2S is actually a diprotic acid, meaning it has two acidic hydrogens. And so therefore it can make H2S or HS minus. And so I can only go one hydrogen at a time. So if I'm starting with S2 minus, which I got from Na2S, then what I can do is write my weak base equation, but only transfer one acidic hydrogen from the H2O over, which means my product is HS minus, not H2S. From there, it's my typical ice table. I just want to say that one more time. So what happened is I knew that the ion I was working with was S2 minus. I added H2O, but when I'm writing a weak base equation and I'm adding H2O, I can only do that by transferring one hydrogen over. So one hydrogen from this H2O comes over, not two. That gives me HS minus as my product as opposed to H2S. And so there, I'm just gonna do my usual 0.080. Okay, now I know that KB is going to equal x squared over 0.080 minus x. Okay, now I got to flip back to my appendix and get my KB. Well, of course, there's no KB for S2 minus. What I do have is Ka1 and Ka2 for H2S. Ka1 for H2S turned out to be 9.5 times 10 to the negative 8th. But that's really for H2S. Ka2 turns out to be 1.1, sorry, not 1.1, just 1, times 10 to the negative 19th. If that's Ka2, that means it's the H2S without one proton, which means it's HS minus. So actually the Ka that I'm looking for here is Ka2. I may have accidentally told you on Friday that we always use Ka1 in a problem like this, but here we can see an example of one that's not true, and we would actually use Ka2. From there, it becomes pretty straightforward. Ka, Kb equals Kw. That means my Kb turns out to be 1 times 10 to the 5th. So I come down here. Okay, now please notice I cannot actually make my assumption here. Times 10 to the negative fifth is actually really large. So I have to actually go ahead and solve the quadratic here. I'll solve for x, which will be my concentration of OH minus. Unfortunately, I have left my graphing calculator at home, and I got annoyed trying to use my phone. So you guys can go ahead and calculate that. You can pause, do the quadratic on your calculator, and you should get the OH minus concentration. If you've done everything correctly, you should get a pH of 12.5. Okay, so please go ahead and pause this video now and make sure that you guys can complete this problem. Okay, so hopefully this all worked out. So remember what made part B different was this idea that it was a polyprotic acid that we were working with, and we had to end up using Ka2, which I actually found quite difficult. Now we're going to see that C is also something different because we end up having a mixture. So I think I'm going to pause this video and just get a clean slate here and then come right back. So we are taking a look at the last problem, which is C, which says 0.045 molar NaCH3COO, which we recognize as CH3. What am I trying to say? Acetate. We recognize it as acetate. Okay. So, but we have these mixtures. So let me take a look at both of them. I think I'm still an eraser. Hold on one second. Okay. So Na. Doing my usual. Breaking it into its ions. Strong base. Weak acid, that's acetic acid. Group 2 strong base. Weak acid. Okay. Now, I notice here that in both scenarios, my weak acid side looks exactly the same. And in both scenarios, these are going to be basic solutions because of the strong base. So I'm going to focus here, but I need to write a base equation. And it turns out that because I'm writing the base equation, I'm actually going to just write the same equation for both components of the mixture. So I can just go ahead and write one equation. I don't have to write two. I'm using my ion like I always do. Acetic acid. I've written it in a different form than before, but it doesn't matter. And I'm going to ice it. Now, the only thing that's going to make this problem different, and I'll let you guys work it out instead of me working it out, is that I actually have to combine my two molarities. I'm going to go ahead and assume 1 liter so I can combine my molarities. So from my NaCH3COO, I get a 0.045 molar CH3COO minus. But from my BaCH3COO2, notice that for every one of my barium acetate molecules, I get 2 acetate ions. So I'm not going to say 0.055 molar. Instead, I'm going to say 0.110 molar. So that's the 0.055 times 2. So the acetate concentration from the barium acetate is actually 0.110 molar because it's in that 1:2 ratio. So total, I have 0.115 molar to start here. And I think from here you guys should be able to work out this problem. Of course, I'll